welcome to this particular lecture, and what we are discussing right now on the diffusion equation, or rather the discretized equation for the diffusion term. So, what we have done so far, just to give you a brief idea before we begin with the exact lecture for today, is that we have taken the diffusion equation for Cartesian orthogonal grid, then we have done the non-orthogonal system, and right now we are dealing with the non-orthogonal unstructured system. So, if you look at what we have obtained in the last class, is this is what we obtained and stopped for the unstructured grid system or the non-orthogonal unstructured grid system. So, this is the final discretized equation that we obtained, and if you look at this particular equation, it looks exactly similar to your orthogonal system or non-orthogonal, non-Cartesian orthogonal system. So, the equation system actually looks similar. So, that is what one of the advantage of this finite volume formulation, that you can have a similar kind of discretized equation. So, only one discretized equation like the one which is shown here, so that would work for. So, essentially whatever system you have, you end up getting AC phi c plus f goes over all the element, neighboring element equals to BC. So, that is one equation that works for everybody. It works for my Cartesian orthogonal system, non-Cartesian orthogonal system, non-orthogonal unstructured system. So, for each of these system, the end discretized equation look exactly similar. Where it differs in calculation of these coefficients of AC, AF. Here F goes for neighbor elements. So, essentially the elements which are surrounded of that particular element C, where the discretization has been taken place or the discretization is being carried out, and the contribution from all these neighboring elements are going to come in the discretized system. This is the algebraic system which will finally lead to Ax equals to B. And while you compare all these different kind of system, you only get different coefficients, but once you come down to non-orthogonal system, there will be one more extra term which is very important term, is called the cross diffusion term. So, this contribution from this particular term goes in the source term. So, this is an added contribution which comes due to non-orthogonality, and that one has to take care while doing the non-orthogonal grid system or the unstructured system. And we have already seen that the surface vector, which is the surface normal vector, having two different component, EF plus TF. That means one component provides you or gets you back the orthogonal contribution, other due to the non-orthogonality. So, this is where all these system will differ from each other, and the contribution would show up in the calculation of the coefficient. So, this is where we stopped, and now what is important is that while dealing with the Cartesian system or the non-Cartesian orthogonal system, we have seen how to implement the boundary condition. Similarly, non-orthogonal unstructured system also will work out how to implement the boundary condition. And once you have worked out the boundary condition, because as I keep on reiterating the fact, this particular equation is valid for any interior element or cell. This is not valid anything which actually exists at the boundary or anything which is associated with the boundary face. So, for the boundary face or the boundary element, some special treatment is required. Although the governing equation is going to be the same, or rather the discretized equation is going to be the same, only contribution due to boundary treatment they will turn up. So, being said that, we will now look at for this non-orthogonal system, non-orthogonal grid, we will look at the first type of boundary condition is the prescribed boundary condition or Dirichlet boundary condition. Okay. So, this is where you have given the phi. So, if you consider a surface like that, this is a surface like that or element like that, where it is center is C, it goes to this boundary which is B, and this vector is E, then you have a normal vector in this direction which is the direction of the surface vector, and this is the connecting distance, and this distance would be D C small b, and that is the boundary face. So, this is the element which we are interested in, and that is the centroid C, and this is the connecting line between the point B, and there is a surface vector which is acting here along this direction n. So, now we implement, but one thing one has to note here, even while you implement the Dirichlet boundary condition or Neumann condition, you need to account for the cross diffusion term. So, essentially important point is that need to account for cross diffusion term, okay, which is also arises at the boundary faces. Now, this happens whenever the surface vector which we are looking at here, they are not collinear along the connecting lines. So, cross diffusion term will appear. So, now the system which we are dealing with at the boundary is JB dot SB, which is gamma B del phi by B dot SB, which one can write minus gamma B del phi B dot EB plus TB. That means my surface vector at the boundary having two component EB plus TB, and if one has to look at it, this would be the direction of EB, and this is how it is going to be TB. So, that is the decomposed or the components of that. Now, if I write that, it is gamma B phi B minus phi C by D CB EB minus gamma B del phi B dot TB. So, which in terms of coefficients, it is flux CB phi C plus flux BB. Now, flux CB where is equal to gamma b dB. dB is, as we have defined so far, dB is the geometric diffusion coefficient, and this would be gamma b dB phi b minus gamma b del phi b dot Tb, and our dB is nothing but Eb divided by dCb. So, once you put these things back and the system, you get your, if you put these things back in this particular equation, you get back AF equals to flux FF, AC equals to small NBC flux CF plus flux CB, and BC equals to QC VC minus flux BB minus NBC flux BF. So, given a specified boundary value, one can get all these final coefficients. Now, once you get that, the second kind of boundary condition would be Neumann type of boundary condition. So, Neumann boundary condition, it is, thing is that in this particular case, this follows exactly like orthogonal grids. So, the Neumann case, one can follow the procedure in this case. So, flux is user specified. So, one can follow the procedure exactly that we have derived for orthogonal system. So, if you do that, just the extra term which is going to be added at the source term. Now, the third kind is the mixed boundary condition. Now, for mixed boundary condition, you have both specified value phi specified and flux also specified. So, both of them are specified. So, in this case also one can derive that boundary condition. So, once we do that, we use the similar kind of example like what we have drawn right now, that the element is there and you have that boundary face where you get the, this is E, B, this is where the SF and N, and here at this face, this is the boundary face, you have both phi specified and you have both flux specified. So, you can derive the system like JB dot SB, which is going to be now gamma B phi B minus phi c d c b E b minus gamma b del phi b dot T b. So, again your surface vector is having two component, one is E b, another is T b. So, this is essentially E b plus T b. So, that is what it shows up here, which is H infinity phi infinity minus phi b S b. Now, from here you get phi b, which is H infinity S b phi infinity plus gamma b E b divided by d c b phi c minus gamma b dot T b, and denominator you get H infinity S b plus gamma b divided by. So, that is what you get for phi b at the boundary. So, once you get that, you use this in this particular equation. So, now you put in back in that particular equation and you get now your J b dot S b is, so it will get slightly involved now, because you will have some cross diffusion term associated with this calculation, which was not present in the case of orthogonal system. But again the non-orthogonal system is more generic in the sense the special case of this is the orthogonal system. Now, you get H infinity S b gamma b del phi b dot T b divided by H plus gamma b E b divided by d c b. So, one can think about this is my coefficient of A b, and this one can write S b comma due to cross diffusion C d here essentially represent cross diffusion. So, I will represent this one is in more compact form, right, flux C b phi c flux V b, and if you equate the coefficients, you will get, by equating the coefficient between these two, you get flux C b equals to H infinity S b gamma b E b divided by d C b H infinity S b gamma b E b, and what you get for flux V b is minus flux C b phi infinity minus H infinity S b gamma b del phi b dot T b divided by so this is what you get for these coefficients. Now, the thing is that since this is for the non-orthogonal system, if the cross diffusion coefficient is 0, that means from here you can always get back the similar thing for orthogonal system, and that is a special case of non-orthogonal system where this particular term actually goes to 0, then everything else look exactly similar for orthogonal system. Now, so the modified coefficients in the system of the discretized equation. So, the modified coefficient in discretized equation look like AF would be flux FF minus gamma F EF by dCF, and AC equals to flux CB plus F goes from all the faces flux CF, and BC, which is the source term, it will be QC BC minus flux BB minus C flux BF. So, that is what you get when you apply all the boundary condition. So, essentially what you get when you deal with all this orthogonal or non-orthogonal system, your equation, discretized equation looks same. Then when you come down to the boundary element, as per your boundary condition, so you use that boundary condition and get this modified coefficients as we have derived for all these cases individually. Whenever you have a specified phi value at the boundary face, that means the Dirichlet boundary condition, you obtain the different coefficients. When you have the Neumann condition, that time the flux is specified, so you obtain the flux condition. Then when you have a mixed condition, you get the coefficients modified accordingly. And non-orthogonal system is more generic in the sense, because if you get this term of the cross diffusion term, which are the contribution due to TB, if they are 0, it essentially becomes orthogonal system. Now, there would be one important thing to discuss is that skewness. So, that is something which will be very important to discuss, because in your discretized equation you need to have, or it is very much necessary to estimate the value at the faces. Now, when you estimate the value at the faces, so essentially you estimate the value at face. Now, that could be of average value or it could be in different values. At different steps of the discretization process, linear variation of the variables are essentially assumed. So, that is most common, that which we have discussed, linear variation of the variable which are essentially assumed. Now, if this linear variation is extended for the other cases, then there are certain issues for specific cases. So, that time we can avoid this linear variation and come up with something else. So, the common practice is essentially is that you do a linear interpolation profile to estimate the phase value. So, that is the common practice. Now, when the grid is essentially, as long as you have no problem with the grid, there is no issues with this linear interpolation and you can get an very good estimate. But if there is a small skewness, for example, let us say you have an element like this, okay, and that is your connecting element. So, you have C here, you have F here, so they would be connected with this line. So, this is F prime, and there would be another point which is essentially going from there, which is F, and this is also connected, and the surface vector will act as SF. So, if you look at this particular element or the example which we have drawn right now, where the intersection point of segment of C and F, that intersection point is F prime, which does not coincide with the face centroid of that F. So, essentially this is my face, and the face center actually lies at this point F, and the connecting line between the centroid of C and the neighboring element F, they lie at F prime. So, they do not lie at the same location. So, there is a offset, or essentially this is the skewness. So, now in order to keep the accuracy, or in order to maintain the accuracy of the discretization method, so in order to do that, maintain that accuracy of the discretization method, so all phase integration need to take place at point F. So, essentially the integration needs to be taken place at point F. Okay. So, what happens, a correction for the interpolated value at F prime is needed in order to get the value at F. Why? Because the connecting line between C and F, they are not correlated, or they do not lie on the same point. F and F prime are essentially different point. So, the skewness correction can be derived. So, this is the skewness, and the skewness correction can be derived for phi f at point phi is that phi f prime plus delta phi f prime dot d f prime f. So, which essentially the distance of these two, between these 2 points f and f prime, and considering the value at f prime. So, this is a skewness corrections. So, and d f prime f is the vector from the intersection point f prime to the face center F. So, that is the correction that one has to do. So, with that correction one can interpolate the value at this point. So, this is very natural when you have some sort of a skewness or skewness in the grid, this kind of small skewness correction needs to be taken place. So, thank you. We will discuss our other things in the next lecture.